morning. So, we will start with our second lecture. In the last lecture, we looked at some basics of fluid flow. We defined fluid, we defined continuum, and we also looked at certain fluid properties, density in the context of continuum, and also the velocity field. We also introduced the concept of Eulerian and Lagrangian approaches of fluid mechanics. So, in the lecture 2, we continue with the flow field. There are different ways to visualize a flow field. So, let us take an example of the velocity field. Now, in the last case which we have demonstrated in the last lecture, the flow field was a steady 2-dimensional, but now we have taken an unsteady flow field. So, it has a t component here, you can see here, and just to remind ourselves, the velocity is basically a velocity at a point, because we are always following a Eulerian approach of fluid mechanics here. So, this is a velocity of a point, velocity at a point. Now, so the x component of velocity I hat is the unit vector in x direction. So, x component of velocity at time 0, everywhere it is 0, because it is minus x into t. As time increases, it increases. The y component of velocity is independent of time, but it increases in the direction of y as y increases. So, it is a 2D unsteady flow. Now, this let us see this flow field for this slightly changed situation. The first thing which we can use to visualize the flow field is to look at the streamlines. We have defined streamlines in our last lecture. Basically, these lines are lines, tangent to these lines are actually the direction of the velocity, and perpendicular to these lines there is no flow, because the velocity is tangential to the streamline. Let us look at the velocity vectors and streamline at a time 1 second. So, basically if you plot it, it comes like this. The velocity vectors are shown in black, whereas the streamlines are shown as red lines. In this particular situation, of course, these lines are straight, but it need not be straight, as we will see very soon. Now, everywhere you can see that if you draw a tangent to the line, it falls in the direction of the velocity vector. Again, we can see here that at t is equal to 1 second, this velocity x directional velocity is minus x, whereas the y directional velocity is minus y. So, the velocity field is something like this. All the velocities, as we go far from 0 comma 0, which is shown here, the velocity values increases and everything is directed towards the origin. So, this is basically the velocity field. Now, if we go to a time, a higher time, that is, let us say t is equal to 5 second, the velocity vectors and streamlines, let us see how it looks like. So, what we see is it demonstrate complete it demonstrate the unsteadiness of the flow. The flow field has completely changed at a higher time, and the streamlines have also changed. So, that means the streamline actually changes with time as the velocity field changes. Mostly the streamlines are used to visualize the flow field when we are doing a analysis. So, it is very useful to see the direction of the flow, to understand the direction of the flow using the streamlines. It is difficult to get experimentally the streamlines. So, for visualizing a flow field experimentally, we use different kinds of lines. We will see that in the next slide. So, another line which is used for visualizing flow field is called timeline. So, let us look at the velocity vectors and timeline at t is equal to 0 and 0.5 second. before we go into this, let us see, let us define what is a timeline. Timelines are basically lines introduced in the flow and looked at the line, the deformation or the change in the line as the flow evolves or as the time changes. So, you introduce a straight line, for example, in the flow and see how it changes as the time passes. We will look at why, what is the significance of this and how we can experimentally visualize it. We have taken the example of a velocity field as shown here. This velocity field is like x directional velocity is proportional to y, that means at y is equal to 0, the velocity x directional velocity is 0, and as you move along y axis the velocity increases, and the y velocity is actually identically 0 everywhere. Now, so we let us say this is basically if we join this circles, the red circles, we will get a line. We say that this is one line, and now at t is equal to 0, if we look at the same line at 0.5 second, it will look something like this. So, this is an example of a timeline. How is it useful? If you look at the velocity variation along y direction, the x directional velocity is linearly changing in the y direction. It is directly proportional with the y coordinate. If we look at the timeline, qualitatively it is very much representative of the velocity profile. So, experimentally actually you can generate this streamline by releasing some particles from here. Let us say we release bubbles from the bottom of this is a flow over a flat plate. This is very similar actually to the flow over a flat plate, not with respect to the velocity profile, but with respect to the no slip condition on the bottom wall, on the bottom surface. So, now if you release bubbles, if there was no flow, the bubbles will actually follow this line, and when there is flow, gradually it will get shifted. The bubbles which are located very close to the wall will almost they will not move, or they will move to a very small distance far away from the wall as the velocity is higher. So, they will move through a larger distance. So, if we want to get an idea about the characteristics of the velocity profile, we can use these timelines. To demonstrate this further, we take another velocity field. So, now instead of saying the velocity field in the x direction, which was directly proportional to y in the previous case, now it is proportional to square root of y or y to the power half. Y velocity or Vy is again identically 0. Let us see what happens to the timeline under this situation. So, now we again draw the timeline at time 0, that is the line introduced into the flow field, and what happens to it after 0.5 seconds. So, this is at time t is equal to 0. You can imagine it as bubbles released from the bottom of this plate, and it rises in absence the way it rises in absence of a flow. Now, as the flow starts, as the flow field is established, in that under that condition the bubbles move and they take the positions in something like this, which is different from the first case. So, in the second case at 0.5 second, the positions the bubble take again is very similar, will become very similar to the velocity profile. So, this kind of visualization actually helps us to directly look at the characteristics of the velocity profile in a flow situation. So, we have seen streamline in the last slide, which is useful, more useful for visualizing a computed flow field. Timeline is useful to look at the velocity profile experimentally. There are other ways of visualizing a flow field. So, we will introduce that in the next slide. For doing that, what we do is we consider this domain, this fluid domain, and now we consider a particular region. So, this is basically a particular region in the flow, a small region in the flow. We consider now a fluid particle in that region. So, if we introduce a particle in this region in a flow field which is established here, it will actually start moving, because there is a flow established flow field in this domain. So, the particle follows the flow field and moves to the new region, then again it goes to its next position. So, in this way it moves. The flow field is, let us say, such that it takes the particle in this particular trajectory. The line which is formed by following this particle is called a path line. So, this is also useful to see how the particles are moving within a fluid, particles are moving within a flow. Experimentally it is easier to get this kind of path lines. You can inject a dye like we did here. Let us say this blue particle represents a blue dye. So, we inject a dye at this location and then track it as it moves within the flow field. So, this gives us a path line. Like in the case of streamline, the path line is also in an unsteady flow, it is a function of time. For example, the particle, if it is an unsteady flow, a particle introduced at the same point at the next instant of time need not follow the same trajectory. So, the path line will not be the same. We will demonstrate this fact in this next figure. In this figure, let us now say we have this blue particle introduced into the flow. As it is introduced, it moves to its new position, which is this, and at that time instant we introduce a second particle which is different in color. Now, this particle which is introduced at the second instant of time can follow, if the flow is unsteady, can follow a different trajectory. So, you can have a different path line for the particle injected at the same point. Let us say at that second instant, when this first particle has again moved to its new position and second particle has moved from the first to the second position, we introduce another green particle at the third instant of time, and then we follow it. It can again go in a different way as the flow field is unsteady. Now, each one of this, according to our previous definition of path line, each one of this is actually a path line. It is the path taken by a particle introduced into the flow. So, all this are actually path lines. All the three lines shown by different colors are path lines. We can define another line by joining this locus of all the particles which passes through, which are introduced initially from the same point, and this line is called a streak line. So, basically this is the locus of particles which has been injected at the same point. Now, if this field was not unsteady, like in the case which is demonstrated here, then this particle would have actually fallen in the trajectory of the first particle, in the path line of the first particle. The third particle, which is green in color, would have also fallen in the path line of the first particle, and if we join those lines, if we join the locus, if we take a locus of all the particles, then we will actually get the path line back. So, it can be seen that in the case of a steady flow, the path lines and streak line actually superimpose with each other. The example, the experimental method for visualizing streakline is a smoke visualization. That means, you are in the case of pathline, we injected dye, small drop of dye, and see how the trajectory taken by the dye, whereas in the case of streakline we keep on injecting some seeding particles or some dye or smoke at a particular point and keep on tracking the trajectory taken by the entire smoke trajectory. So, this smoke visualization is an example of a streakline. So, just to revise what we have demonstrated in the context of visualizing a flow field, we have introduced the concept of streamline. The streamlines are actually lines to which the velocity vectors are tangent. Timelines basically are lines in a flow field evolving with time. So, if you introduce this need not be in a particular direction, but you just introduce a line into the flow field and see how it evolves with time. It is useful to get if you can thoughtfully introduce a line at the initial time instant, you can figure out the velocity profile by looking at the evolution of the timeline. Path line is basically a trajectory of a fluid particle. So, path line pertains to a particular fluid particle. Streakline is locus of the fluid particles passing through the same point. Now, as we have said before, we can see that in a steady flow all these lines no, not the timeline, but the streamline, path line and the streakline, they actually coincide with each other. In an unsteady flow, like demonstrated in this second box, this second part of this slide, this right part of the slide, they could be quite different, the path lines could be quite different. In an unsteady flow, they will not overlap with each other. The second, so we have after introducing the continuum concept, we have looked at different field of different properties. We have looked at the velocity field, we have looked at how to visualize the flow by looking at different approaches. Let us now look at the stress on the fluid element or the stress field in the fluid. So, to look at the stress on a fluid element, let us take this as our reference system x, y and z, and we consider a 3-dimensional fluid element as shown here. Now, if we look at the stress on the fluid element, first we talk of normal stresses, like the stresses which are perpendicular to the plane on which it is acting, or we can say it in a different way, we can say the stresses, the direction, the orientation of the stress is parallel to the direction of the plane. What is meant by direction of a plane? The direction of a plane is actually the direction of the normal drawn to the plane. So, if you take this plane and draw a normal, its orientation will be same as the orientation of the normal stress. So, this is an element on which normal stresses are shown. In fact, you can see the nomenclature has a certain indication. It shows it says sigma xx instead of sigma x. It means that this stress acts in the x direction and also in x plane. We will see this further when we demonstrate the shear stresses. So, now the yellow arrows actually shows the shear stresses acting on this fluid element on the 3 planes which are visible in this view. Let us take an example of this tau yx. So, this tau yx is actually acting in x direction and it is acting on the y plane. What is meant by y plane? The y plane actually means if you draw a normal to this plane, it will be parallel to the y axis. So, the first one represents the plane on which it is acting, the second one x represent the direction in which it is acting. So, similarly you can name this as tau y z, tau x y, tau x z, and so on so forth. So, these are the stresses which are acting on the fluid element. There are both normal stresses and shear stresses. If you have to represent these stresses in a compact way, then you can use this stress tensor. So, the stress tensor is actually it has 9 components. Now, before going into the details of that, what we see is when we represent a force, actually it is a vector quantity, it has three components. When we represent a stress, we need 9 components. The reason behind this is when we represent a force, it is just the force, whereas when we represent a stress, it is force per unit area. So, we have to bother about how the area on which the force is acting is oriented to the direction of the force. So, that actually distinguishes the stress into shear normal stress and shear stresses. So, even in a 3-dimensional situation, like this element is a 3-dimensional element, you can have 3 normal forces like this, and you can have 3 shear stresses acting in 3 different directions. Of course, you will have complementary stresses acting in the other planes, in the parallel planes which are not visible in this view. So, when we talk about stress, we can just cannot explain the state of stress just by using 3 components. We have to use the components of the normal as well as the shear stresses. That is why we use a stress tensor rather than a vector. If we talk about a stress tensor for a 2D element, of course, we will not have the normal stress in the z direction and the shear stresses acting in the z direction. So, basically if you see, this is the normal stress sigma zz in the z direction, and these two are the shear stresses either in z plane or in the z direction. So, we do not have this in a 2D element, and the shear and the stress tensor looks like this. Now, you have a stress field within the fluid, within the entire fluid, like which is demonstrated in a fluid particle or a fluid element. The important thing to consider now is how this stress, how the stresses which are shown here, demonstrated here, how do they relate to something which we can talk about in terms of a flow, like fluid velocity. For solids, we know that the stress is related to the strain by using the Hooke's law of elasticity, of course within the limits of within the elastic limit, that stress and strain are linearly proportional. Let us see how this law transform in the case of a fluid. We have seen in our first lecture that the fluid behaves differently than a solid when a shear force is applied to the fluid. Here let us see how the stress relates, how can we express stress in terms of something like velocity, or what is the complementary part of Hooke's law for fluid. Of course, this is this I already told that stress and strain are proportional, and E is basically the elastic modulus. So, E is basically a property of the it is a property of the solid which characterizes its elasticity. We also said that solids are elastic whereas fluids are viscous. So, a similar property should be there for fluid. which can correlate the stress with something like deformation. So, we will see that. Before going into that, let us look at a 2D element instead of the 3-dimensional situation, which is more complicated. So, for fluids, let us look at a 2D element subjected to shear stress. We have only considered shear stress here because the normal stress is important only when the compressibility comes into picture. We will talk more about towards the end of this first part of the introduction to fluid flow about compressible flow, but essentially this part relates, normal stresses relates more to the towards the compressibility. Let us see the shear part. How does the shear part relates to the deformation of the fluid, because under the action of a shear force the fluid constantly flows, or it so let us see how, or constantly deforms. So, how that deformation can be linked, or what is the law defining the relationship between the shear stress and the deformation. So, we take this element at a time t, a force act on this 2D fluid element. Of course, it will deform, means its shape will change at t plus delta t, and we can take delta alpha, the angle made by this edge of the fluid element with its initial direction as the deformation. So, it gets deformed. The question is how we can relate this to stress, shear stress. Okay. We will soon see what is a Newtonian fluid, but we come back to our discussion of the element. We have taken the element fluid, 2-dimensional fluid element introduced in the previous slide for time t plus delta t, when the fluid element is already deformed. Let us say the top part has a velocity delta u, and the size of the fluid element is delta x and delta y. Delta L is the deformation, the linear deformation of the fluid element. Now, let us look at this part separately. So, if you look at it, you can take this part, this angle is delta alpha, this side, this is the initial edge of the fluid element, this is delta y, and delta L is the linear deformation. So, you can write a relationship between these 3 parameters provided delta alpha is small. So, you can write delta alpha is equal to delta L by delta y. Okay, this angle is this arc, it is for small values of delta alpha, this is like a arc. So, this arc by this radius, for again for small value, this difference between delta y and this edge can be is negligible. You can write delta alpha is delta L by delta y. Delta L deformation can be written as delta u into delta t. Delta t is the time spent, delta u is the velocity of the top edge of the fluid element. And so, now you can write that d alpha by dt, that is the rate of deformation, can be related to the velocity gradient. So, delta d alpha by dt can be written as du by dy. So, why are we doing all this? We want to get an expression for rate of deformation in terms of velocity, because for the flow field, by the flow field we mainly mean the velocity or its gradient. So, we finally want to relate stress with velocity or its gradient. So, for fluids, a 2D element subjected to shear, we can the law says, like the Hooke's law, this law says that the shear stress is actually proportional to the rate of deformation. Okay. So, rate of deformation is du by dy. So, that means the shear stress is related to the velocity gradient as du by dy, and you can write this also as an equation by introducing a constant mu. So, you can write tau yx as mu into du by dy. This mu is the viscosity of the fluid. So, this is very similar. In the case of solid, the property which or the constant which related the stress with the strain was elastic modulus. Here we have viscosity, because the fluids are viscous, whereas solids are elastic within its elastic limit. Of course, this is called dynamic viscosity, and this law is called Newton's law of viscosity, which is a complementary part of Hooke's law for applied to fluids. The property viscosity, of course, it has a different unit than elastic modulus, because elastic modulus, you see, it is it relates stress and strain. So, it has the strain has no unit. So, elastic modulus has the same unit as stress, it is Pascal, whereas this actually it relates viscosity relates shear stress with rate of deformation, a rate factor is there. Okay, so, this unit of du by dy is 1 by second. So, unit of dynamic viscosity is, this is Pascal. So, Pascal second. So, we have demonstrated here the viscosity of some familiar fluids. Let us take a little detailed look at the values of the viscosity. So, let us take water at 20 degree centigrade. The viscosity in Pascal second is 10 to the power minus 3. So, of course, Pascal is actually I am sorry, is actually SI unit. So, it is Newton per meter square. So, water at 20 degree centigrade has a viscosity of 10 to the power minus 3 Pascal second. You can also represent this in the CGS unit, which is shown here. The viscosity of water at 20 degree centigrade is 1 centipoise. Poise is basically dyne second per centimeter square, and if we write it as centipoise, that is 10 to the power minus 2 into poise, 10 to the power minus 2 dyne second per centimeter square, because the value of water becomes 1 if you write it as centipoise. So, it is very easy to remember also, water at 20 degree centigrade is 1 centipoise, which is 10 to the power minus 3 Pascal second. This also gives us, helps us to remember the relationship between centipoise and Pascal second. Now, we take water at 90 degree centigrade, it has lower viscosity. So, what we see for liquid, so the viscosity, the property which we got from the relationship between stress and the rate of deformation, we see that this is also a function of temperature. As the temperature increases, the viscosity decreases, but this is only true for liquids, where the intermolecular force loosens if you go to higher temperature. Let us take an example of air at 0 degree centigrade. So, you can see it is very inviscid. Of course, we know that air is much inviscid. So, to look at the value, it is 100 times 1 by 100 times that of water. So, water is 100 times viscous than air. So, it is about 1.75 10 to the power minus 5 Pascal second, or so much centipoise. But one important thing to note here is the same air at 27 degree centigrade actually has little higher viscosity, not very significantly different, but the trend is different from that for liquid. So, this is a characteristics of gases that they have, for them the viscosity actually increases with increase in temperature. We have taken some other familiar fluid. We have taken the example of glycerol at 20 degree centigrade. You can see it is highly viscous, it is 1.2 Pascal second. So, if you take water, it was 1 millipascal second, whereas glycerol is around 1 Pascal second. So, 1000 times that of water. Okay. So, similarly here it is 1 and 1200. So, if you want to, this is useful, because if you want to study the effect, experimentally study the effect of viscosity on certain process or certain things, then you can use this combination. You can use glycerol, repeat the process with same maybe other conditions with glycerol, then you can see what viscosity does to that effect, to that particular parameter. In fact, we can define some parameter, another parameter called surface tension. This is a useful information for an experimentalist, that you see if you look at the surface tension of glycerol, it is very close to that of water. So, if you want to keep the surface tension same and study the effect of viscosity, you can do the same experiment using water and glycerol. You will know what viscosity does to them. Of course, this is little out of context, but this is useful to know. Experimentally, it is very difficult to keep other it is very difficult to change only one property to see the effect of that property, because if you change the fluid, then a lot of other properties also changes. Another example is propanol. So, this has a very this is another hydrocarbon, and it has very similar viscosity as water, as you can see here. So, we saw that fluids are basically dissipative, and they show display viscosity. Some of the values of viscosities are displayed here. So, this brings us to the end of the second lecture. In this lecture, we have looked at velocity, field, and different types of parameters to define a velocity field, like the streamline, which is useful for visualizing a fluid flow, then pathline, timeline, streakline. We saw that the pathline, streamline, and the streakline becomes the same in the case of a steady flow. We also looked at the stress field, the stress on a element, on a fluid element. We looked at the stress tensor, and then we have also introduced how stress relates to rate of deformation in the case of a fluid, and which is also known as Newton's law of viscosity, and the fluids which obey this law of Newton's law of viscosity are called Newtonian fluids. In the next lecture, we will begin with non-Newtonian fluids, which do not obey the Newton's law of viscosity. Thank you.